Good morning, students. Today we will discuss about the Maxwell's thermodynamic equations and potentials. So, last class we have been discussed about the Maxwell's equations, 4 Maxwell's equations. So, here we will discuss about that in detail. Maxwell's thermodynamic equations, 4 equations are there. Okay. So here how you will get what is the derivation part of this Maxwell's thermodynamic equations. So, what are the applications are there? So, we need to know about that. So, myself is Dr. V. Srinivasarao, Assistant Professor of Physics, GTC Uppalli. So, here Maxwell's equations. Okay. So, which is what is the derivation of the Maxwell's relations? So, how you are going to be deducing these equations from the differential form of the thermodynamic potentials. So, you know about these thermodynamic potentials in previous class. So, one is that here internal energy, du and dF values, Helmholtz free energy, enthalpy, Gibbs free energy. Okay. So, from these how you are going to be deduce these equations. Okay. First of all, discuss about that here. What is the differential form of the internal energy? So, d equals to TdS minus PdV. So, what is the basement of this equation? So, the basement of this equation is here first law of thermodynamics as well as the second law of thermodynamics. So, from these equations we have been derived that internal energy d equals to TdS minus PdV. You need to do the practice, okay, then only you have to remember these equations. So, here by considering this internal energy equation d equals to TdS minus PdV. So, what is the total differentials of this equations? So, you know pretty well the basic equation for this dz equal to, let us consider that here. In place of z, you can put it down here u, f, h as well as the z values. First of all, you need to know that here. So, total differential form here dz equals to dou z by dou x of y into dx plus dou z by dou y of x into dy. So, here the other form, so that is the dz equals to you know that here that is dz equals to m dx plus n dy. So, by substituting these equations in the above form, so you know that m value equals to dou z by dou x of y as well as the n value equals to dou z by dou y of x. Let us consider that the internal energy equation d equals to TdS minus PdV. So, in this by substituting here what is x value, what is y value and what is z value. Here z is the u, x is entropy for here whether it is for m as well as the n equation, that is the m dx plus n dy. So, that is in the form. So, by substituting here the values, m value is t and n value is minus p and z value is internal energy u value and x is entropy s and y is volume v. So, by changing this with respect to the entropy as well as the volume v, so we have been derived that equations T value as well as the pressure P value. Since we know that for functions with continuous second derivative, so what are the mixed partial derivatives which are identical? Okay. So, here partial differential equations. So, second order dou by dou y of dou z by dou x of y which is equals to dou by dou x of dou z by dou y of x. So, that should be equals to dou square z by dou y dou x left hand side which is equals to here dou square z by dou x dou y. So, therefore, we can see that here dou by dou v of, so here what is z here, u, okay. X and y is entropy S as well as the volume V. So by substituting these equations, so dou by dou v of, here dou u by dou s of v, which is equals to dou by dou s of, in place of x we substituted here s, okay. In place of y we substituted v, in place of z internal energy u value, and here what is the x value, s. By substituting all these equations, we have been derived that dou by dou s of dou u by dou v of s. Therefore, we can give the equation for this dou t by dou v of s equals to left hand side, which should be equals to minus of dou p by dou s of v. So, like that here we can derive the other equations also. So, what is the derivation of the Maxwell relation from the Helmholtz free energy, other one. Before that, internal energy du value, okay. One Maxwell's equation is derived. So you can see here first equation. So dou t by dou v of s equals to minus dou p by dou s of v value. Similarly, by considering the second differential form, what is that? Second differential is Helmholtz free energy. What is that value? df equals to minus s dt minus p dv. In first class we have been already derived these equations, okay. So from these equations only we have been deriving these Maxwell's relations of the thermodynamic equations. So let us consider that minus s equals to here dou f by dou t left hand side, which is a function of volume V. Similarly, minus p, pressure p value should be equals to dou f by dou v of t. So what is the symmetry of the second derivation? So that equation is dou by dou v of dou f by dou t of v equals to dou by dou t of dou f by dou v of t. Therefore, by combining these equations, we will get here what is the value of dou f by dou t here. Dou f by dou t of v equals to minus s. So here you have to substitute, okay. So what is the value? Minus s, and here dou f by dou v of t value is minus p. Minus and minus get cancelled. Therefore, the equation becomes dou s by dou v of t equals to dou p by dou t of v. So this is the second Maxwell's thermodynamic equations. So which we have been derived from the here Helmholtz free energy. First equation is from the internal energy. Second one is from the Helmholtz free energy. So how to derive these equations? Okay, you need to remember. You need to do the practice. Then only you can able to remember. So here the other two. So what are that? Here Helmholtz. So we have been derived this. Internal energy is over. So here you need to know about that what is the Gibbs function, dg value, okay, and also enthalpy, okay, dh value. So you need to do. So this is the process here, how to do, how to simplify, how to get the differential form. So the other two Maxwell's relations which can be derived from the differential form of enthalpy and the here differential form of the Gibbs free energy in the similar way. So here you need to do the practice, then only you will get these equations. Next one. So what are the Maxwell's equations here? So these Maxwell's equations which can be derived directly from the thermodynamic potentials using first law of thermodynamics. What is the first law of thermodynamics? D equals to TdS minus PdV. So here we have to write it down that du by ds, which is a constant value that you be representing here. So how you have been writing this equation means here left hand side. First equation you can see here d equals to TdS, okay. So, here du by ds or dou u by dou s which is equals to T, and dou u by dou v which is equals to minus P. So, which is a perfect differential. So, that your second order differential equation which should be dou square u by dou u dou s equals to dou u by dou v dou s. So, which is going to be satisfying this. So, that is called here second equation. So, what is the partial differentiation of this above equation, which is v into dou u by dou s equals to T with respect to that here, and du by ds equals to minus P with respect to entropy S. So, here the second order differentiation, that is the dou square u by dou v dou s equals to minus dou t by dou v of s, and dou square u by dou v dou s equals to minus dou p by dou t of s. So, substituting these equations or these values in the equation 1, we will get dou t by dou v of s equals to minus dou p by dou s of v. So, this is the Maxwell's first equation. So, this is the other form. Next, enthalpy by considering H equals to U plus V PV. So, in terms of basic coordinates, dH equals to du plus PdV plus VdP. Okay. So, by substituting a du value TdS minus VdP, there the some cancellation should takes place. So, that what is the final equation, dH equals to TdS minus PdV. So, by the above here process, so that dH by dou s of P equals to T or dH by dou P of S equals to V here. So, by substituting and the same manner here differentiating, so that dou square H by dou S dou P equals to dou T by dou V of S, which is, and also dou square H by dou P dou S equals to dou V by dou S into P here. Why? Because of here dH is a perfect differential equation. So, we can simplify and we are going to be equating these equations, that should be dou T by dou V of here S equals to dou V by dou S of P here. So, this is the Maxwell's second equation. Next one, what is the relation 3 here? So, that is a Helmholtz function f equals to u minus Ts. So, what is the partial differentiation here? By differentiating this equation, then you have to do the partial differentiation. So, what is that here? df equals to here u means du, du means here TdS minus PdV. So, here you will get the TdS, okay. See here, here you will get the TdS u value, that is the first law, we are to be substituting TdS minus S dt, okay. So, here some cancellation should takes place here, that is TdS minus S dt is there. So, that du value is going to be substituting here. So, final equation becomes here df equals to minus PdV minus S dt. Therefore, here du equals to here dq minus PdV from the first law, and dp equals to dq equals to TdS from the second law. So, which can gives the here df by dq of t equals to minus p, and df by dt of v equals to minus s. So, partial differentiation from the above said here with respect to t, as well as the partial differentiation by doing with respect to v, you will get here d square f by dv dt of which should be equals to dp by dt of v, and d square f by here dv dt dv equals to ds by dv of t. Since df is a perfect differential, we have dp by dt of v equals to ds by dv of t. So, this is the Maxwell's third equations, okay. So, all these comes here, first equation Maxwell's first equation, second equation as well as the third equation, we have been derived from the internal energy here du and Helmholtz function df, okay, enthalpy dh, okay. So, from these equations, and another one is also there, that is the Gibbs function dg value is also there. So, we have to consider that here what is the Gibbs function, g equals to u plus here P minus Ts. Okay. So, what is the basic coordinates here? So, by substituting, by differentiating this equation, dg equals to vdp minus sdt. So, same manner we are to be writing here, dou g by dou p of t equals to v and dou g by dou t of p equals to minus s. Okay. So, second order differentiation equation, one is that with respect to T temperature and other is that with respect to the pressure P. So, that here d square g by dp dt equals to dv by dt of P and also here d square g by dou t dou P equals to ds by dp of T. Since dg is a perfect differential form, so that right hand side we are to be equating, that is dou square g by dou p dou t equals to dou square g by dou t dp. So, here the sixth equation is dv by dt of p equals to ds by dp of t. So, this is the Maxwell's fourth equation. Okay. So, how you have been deriving these equations, you need to follow the same here, whatever we have been discussed, the same manner is going to be follows here, but you need to remember that four equations, four differential equations. If you want to derive those four equations, you need to remember here first and second law of thermodynamics. Okay. So, finally, we are to be writing here d equals to TdS minus PdV, that is to be writing here, that which can gives the Maxwell's equations dou T by dou V of S equals to here minus dou P by dou S of V, and second one is the here dA equals to minus S dt minus PdV. So, from this equations we have been derived dou S by dou V of T equals to dou P by dou T of V, and the third equation dH equals to TdS plus VdP. These are the four basic equations. Okay. Dou T by dou P of S equals to dou V by dou S of P, and final equation dg equals to minus S dt plus VdP. So, that should be equals to minus of dou S by dou P of T equals to dou V by dou T of P. Okay. The basement of these Maxwell's equations, four Maxwell's equations, which is from the here these four. Okay. You need to practice, you need to remember, all these are simple equations from the first and second law of thermodynamics only we have been derived with respect to four variables. One is that here PVTS, simply you can remember that PVTS, pressure P, volume V, temperature T and entropy S. From those four variables only, by considering the first and second law of thermodynamics equations, we have been deriving these quantities. So, from this we have been derived first, second, third and fourth Maxwell's equations. Okay. In examination point of view, the examiner may ask you the differential form here, these equations, four equations are there na, dH value, dA, dF, du and dg values. Okay. dg equations, one, this is the differential form. Okay. From the TD equations, you need to how to derive the Maxwell's equations, that is another essay question. Okay. In examination point of view, these two questions are very, very important. Please prepare well. Next, other one is that Clausius-Clapeyron's equations. Okay. What is the Clausius-Clapeyron equation? So, which is a fundamental thermodynamic relation. So, which describes the behavior of vapor pressure of a substance, which is a function of temperature. Okay. So, what is the use of this here? It can describes the behavior of vapor pressure of a substance, okay, and which is a function of temperature. It is often used to understand the phase transition, such as a boiling and condensation for a pure substance. Okay. Next, to derive this equation, you need to know about that what is latent heat. So, latent heat, which refers to the heat energy absorbed or released during a phase transition. So, in phase transition, which is a melting, freezing, vaporization or condensation should takes place here. So, at where? At a constant temperature. So, the heat energy does not result in a temperature change, but which rather causes a change in the state of matter, one to another state. Okay. So, there which you have to refer to the latent heat. So, we can consider and we can take the Maxwell's third equations, okay now. So, which contains dP by dt, change in the pressure to the change in the temperature. So, term which is the purpose and obtaining this equation here. So, Clausius-Clapeyron equation. So, you can see here dP by dt of V, volume V, which is equals to ds by dV of temperature T. So, multiplying both sides by capital T, you can have T into dP by dt of V equals to T into here ds by dV of T. Okay. So, here the T which comes into the equation. So, T becomes TdS by dV of T, where T is a constant. You know pretty well TdS is dq, second law of thermodynamics. By substituting this equation, dq by dV of T. So, that should comes here dP by dt of V equals to dq by dV of T. So, here that should be L by Vf minus V, that is final volume minus initial volume. So, putting here dq by T is L, latent heat, and dV equals to V from B. So, dP by dt of V equals to L by Vf minus Vi. So, this is the Clausius-Clapeyron equation. This question may be asked as a short question. So, important one, you need to remember this equation. dP by dt of V equals to L by Vf minus Vi. Next, another most important essay question is Joule-Kelvin effect or Joule-Thomson effect. So, which you can call it as a here throttling. Okay. So, whenever a real gas which is throttled through a porous plug, so there is always a change in the temperature of the gas. So, that initially you can get a cooling in general, which is referred to a Joule-Kelvin or Joule-Thomson effect. So, here Kelvin and Thomson both are same here, you need not to be worried here. So, this effect which was discovered by first time in 1852 by Joule-Thomson. So, here a porous plug is nothing but a cotton, okay. A cotton is to be chosen here. So, here in Joule-Kelvin expansion of a real gas, that the enthalpy of the gas. So, what is the formula for the enthalpy? H equals to U plus PV, internal energy and work done. So, which must remain constant. That means constant means H value should be 0. So, although there is a pressure difference across the throttling valve or porous plug. So, high pressure to the low pressure. So, here you need to know that here. So, what is a Joule-Kelvin coefficient? So, which is defined as the ratio of the temperature of a gas, to the change in the pressure dP, change in the pressure dP. So, upon throttling at a constant enthalpy, it should be constant here. Okay. So, which is representing here, what is the Joule-Kelvin JK coefficient here? Mu. Therefore, mu equals to dt by dP at constant H. Okay. So, with this expression, that means here JK coefficient, Joule-Kelvin coefficient mu, which can be achieved, that is a Joule-Kelvin coefficient is terms of the basic thermodynamic coordinates from the enthalpy and second TdS equations. So, there are two TDS equations, so first TDS equation and second TDS equations. So, these TDS equations which are derived from the Maxwell's equations, 4 Maxwell's equations. Okay. That is why here you need to remember all these 4 equations, 4 Maxwell's equations. So, how these 4 Maxwell's equations comes from? These 4 Maxwell's equations comes from the 4 differential form of the internal energy, enthalpy, Helmholtz free energy, Gibbs function. Okay. So, see here our focus is on that here Joule Kelvin coefficient, how we are going to be here deriving this equation means here enthalpy H value equals to U plus PV. So, this is the first equation. Next, by differentiating this equation, dH equals to TdS plus VdP plus PdV. Okay. So, here P value should be 0 pressure. So, that is why here the same equation dH equals to TdS plus VdP. Okay. So, here by taking the second TDS equation, so what is that second TDS equation? TDS equals to Cp dt minus T into dV by dt of P into dP. Okay. So, by considering this equation, by substituting into equation 1, dH equals to Cp dt minus T into dV by dt of P into dP plus VdP. Again, this equation how we are going to be here simplifying this, here dP is there, here also dP is there. By commoning this factor dP, Cp dt minus T into dV by dt minus V of dP or Cp dt, if it comes to the left hand side, here dH plus minus value should be becomes plus value T into dV by dt of V minus V of dP, and dt value equals to dH by Cp into T of dV by dt of V minus V into dP, where H is a constant means dH equals to 0. Okay. So, substituting this value dt equals to here T of dV by dt of P minus V into dP, but dt value equals to dt by dP of H minus dt into dP. So, we can write it down here. So, dt by dP of H into dt equals to 1 by Cp into T into dV by dt of P minus V, where mu value is equals to here Joule Kelvin coefficient mu equals to dt by dP of H, we know that. So, by substituting here left hand side, so that should be equals to mu, which is equals to 1 by Cp. Okay. So, here what is Cp value? Cp is nothing but a here specific heat at constant pressure. Okay. Not C into P, here C of P suffix. So, which is of T into dV by dt of P minus V. So, this is the equation 3 value. So, here Joule Kelvin equation coefficient which is equals to 1 by Cp into T into dV by dt of P minus V. So, here when Joule Kelvin coefficient is negative, okay, you can achieve a cooling effect. Okay. So, here when if it is a positive value, you can get a heating effect. So, that is to be produced. That means, gas should not be cooled down here, the gas is going to be heated upon. So, heating effect should take place when Jk coefficient value is positive. If Jk coefficient is negative, cooling effect, if it is positive, and if mu value is 0, that means neither cooling nor heating effect is going to be takes place. Okay. This ends our Joule Kelvin effect and Maxwell's equations of which is related to thermodynamic equations. Okay. Thank you.